The last time, شباب, if you look here, we have looked last time, we have introduced to the gas mixing. We talk about the mole fraction, mass fraction, how to convert from mole fraction to mass fraction and the reverse. Also, we learned how to calculate the properties of non-reacting gas mixture, how to calculate a specific heat at constant pressure, a specific heat at constant volume, the gas constant for a gas mixture, and also the molecular weight of a gas mixture, the specific heat ratio. And we have learned actually all of that. And we learned also that the partial pressure or the total pressure is equal to the summation of the partial pressure. We tried to solve some guiding examples. And today, inshallah, we'll be talking about the combustion chemistry, how to write down the combustion equation, and how to calculate the air to fuel ratio. Like, if you look at the combustion process in general, so if we have a combustion chamber, so we have here a combustion chamber. Any combustion chamber, will provide this chamber with the fuel, okay? Plus, we have to provide it actually with the oxidizer. Usually, this oxidizer, may be pure oxygen. In some cases, like in some application of Oxy Combustion, like as I told you, all fuels are hydrocarbon fuel. So usually the fuel is hydrocarbon fuel, have, let's say, the chemical structure, let's say CmHn. So usually it consists of carbon plus hydrogen. Usually this carbon is converted to carbon dioxide for complete combustion, and this hydrogen actually by combustion should be converted to H2O. If we are burning with the oxidizer is only oxygen, then the combustion product will be just carbon dioxide and H2O. We can just cool them down, then we can condensate the water vapor and separate it, then we can capture the carbon dioxide and prevent it actually from going to the atmosphere. Oxy combustion is one of the carbon capture technologies that are actually applied in the industry right now in order to control the emission of the greenhouse gases, mainly the carbon dioxide. So we burn with pure oxygen instead of air. So the combustion product will be CO2 plus H2O. We can condensate H2O, then we can capture the carbon dioxide. But most probably, for all application, the oxidizer is air. Air, we assume it actually as a mixture of O2 plus N2. And the existence of N2 in the combustion process, it should result actually this N will dissociate to N plus N, and it may recombine actually with O and O2 depending on the reaction condition. And those actually NO and NO2, we call them actually as the NOx emission. And they are also a contributor actually to the greenhouse gases, and they contribute actually to the global warming. All of this component plus some nitrogen N2 will be actually in the exhaust system if we are burning with air, plus actually we'll have carbon dioxide, plus have actually some H2O, plus in some rare cases we may have some H2. So if you recombine all of these components, in this case, if I try to separate carbon dioxide, it will be actually very hard and expensive process. So burning with air, but air is available for free. We don't pay money actually to get air. But actually you have to pay money actually in order to separate the oxygen from the air. So actually like membrane separation technologies, in which actually we can separate the oxygen from the air, then we can get pure oxygen, then we can do the combustion process with pure oxygen. Otherwise, if you like actually to use the freely available air, in this case actually will result of this combustion process with combustion product looks actually like this. We have too many components. So in this case, if I want to capture the carbon dioxide, it will be actually a very hard and expensive process. Okay. So here, it is expensive at the beginning. We have to pay to get pure oxygen. And here actually after the combustion, we call it actually post-combustion capture, to capture carbon dioxide after the combustion process, we call it post-combustion capture. In this case, we have to pay money, and we have to add money and invest actually in the separation of the carbon dioxide from all of these exhaust components. Okay, but usually if you are treating the gases after the combustion process, maybe the cost maybe a little bit less than using pure oxygen, but still using pure oxygen in Oxy combustion is an option. Okay, is that clear, Shabab?
Doctor?
Yes.
the image is lower than the sound. I don't know if the other students have the same issue.
Yes.
Images يعني
Yeah, the recording.
delay يا شباب.
Yes.
It's clear for me.
Significant
Maybe.
delay, so you cannot see.
It's clear for me.
Any other one يا شباب have delay in? Do you see myself live now and my mouse is just going? So
it's clear.
clear يا شباب.
Can't see.
طب يزيد يعني just try maybe to recheck or something. So إن شاء الله it will be solved. طيب, usually I encounter this problem from my side. So if there any delay يا شباب just let me know. So any combustion chamber يا شباب we have fuel plus oxidizer. In this case we will have actually the combustion product. Plus we will have actually from this combustion process we have to have heat out of combustion. This is actually what we want. We want the heat, okay? Those combustion product, as I told you, may be a combination actually of carbon dioxide, water vapor, NOx, like NO, NO2, nitrogen, and we may have excess oxygen also. So all of these are actually the combustion product. But throughout this course, Shabab, we'll be considering actually the oxidizer as air, and air is 21% O2 plus 79% Na2, and this is Shabab, the volumetric concentration. This is by volume. We assume throughout this course, usually here, Shabab, we have nitrogen plus oxygen plus some helium, some other different other inert gases actually, and other components. Some carbon dioxide already is existing in the air. But usually throughout this course, we'll be assuming air as 21% O2 and 79% Na2 by volume. If we divide, Shabab, this equation by 21, here I will divide by 21, then in this case, each one molecule of oxygen in the air should have 79 divided by 21, that will be 3.76 Na2. And this is, Shabab, the equivalence of air. Each one molecule of oxygen in the air should have 3.76 molecules actually of the nitrogen in the air in this case. Okay? And based on that, actually, Shabab, this will be considered as our oxidizer while writing down the combustion equation for any hydrocarbon fluid, for any kind of fluid. Okay? But let's consider the first case, how to write down the combustion equation. If we have actually a single hydrocarbon fuel having actually the chemical composition CmHn, how to write down the combustion equation and how to calculate the air to fuel ratio. Okay. So the first case, Shabab, that we'll be considering today, if we have hydrocarbon fuel with the chemical composition, let's say CmHn, CX, Hy, anything. Okay. How to write down the combustion equation. So usually, Shabab, for writing down the combustion equation, we assume actually that we have 1 kilomole of the fuel. So only 1 kilomole of the fuel. I think you are maybe have an idea about this, either for the mechanical engineers. I think you have maybe went through this in MBA 204, and I think actually for the chemical engineering guys, they should be expert in that. So if we have a fuel, let's say CmHn, 1 kilomole of this fuel. 1 kilomole, ya shabab, is the number of atoms of this molecules equal to the Avogadro's number. We say this is actually 1 kilomole of the fuel. Or 1 kilomole actually of any substance. This is 1 kilomole of CmHn plus the oxidizer. We said the oxidizer will be O2 plus 3.76 Na2. This is actually, Shabab, is the oxidizer or the air. They will actually burn together, oxidize together, then we can have the combustion product. But let's look at actually the carbon in the fuel, Shabab. Each one carbon molecule need actually one O2 in order to be converted to what? To CO2. Is that clear, Shabab? For complete combustion. Each carbon molecules or atom need actually one O2, then it can convert actually to CO2. But we don't have actually only one carbon molecule, we have actually M carbon molecule. So that means actually it will need M actually molecules of O2 to give us actually MCO2. This is for the complete combustion. Then in this case, we need M molecules of O2, then it can give us actually M molecules actually of carbon dioxide. Like we have also hydrogen. If we have hydrogen, 1H2, that need actually shabab half O2 in order to give what shabab?
H2O.
Exactly, that will be giving actually H2O. But in this case, we don't have, in this case, one molecule of H2. We have N from H, that means N over 2 from H2. Then we have to multiply the here with the whole equation by N over 2. So this will be N over 4, and here we have N over 2 H2O. Then we need here plus the N, we need actually N divided by 4 to give us actually here N over 2 multiplied by H2O. As you know, Shabab, the equation, the combustion equation, has to be balanced based on the law of mass action. Energy or mass cannot be created or destroyed. So the number of moles for the reactant should equal to the number of moles of the product for any species. If you look at the number of moles of molecules of carbon at the inlet, at the reactant, should be the same number of molecules of carbon at the product. Unlike this actually for any other species. And also the mass of any molecule should equal to mass of reactant should equal to the mass actually of the product, because mass cannot be created or destroyed. Mass cannot be created or destroyed like energy, but energy can be converted from one form to another, but it cannot be also created or destroyed based on the law of mass action. The only case, Shabab, that we can have destruction of mass to be converted to energy based on the Einstein law, energy equal to half m multiplied by c squared, and this actually is applied for bodies that are moving with a speed more than the speed of light. Okay, so if we have a body that is moving with a speed more than the speed of light, and this has been tested, some protons in some labs has been tested, very small mass, this can be, in this case, the mass of the body itself can be converted actually to produce energy in order to move this body with a speed more than the speed of light. This is the only way we can have mass can be destructive to energy. But otherwise, in our normal life, with a speed less than the speed of light, in this case, mass cannot be created or destroyed. Okay, so if we have fuel, CmHn, that will need actually M plus N over 4, O2 plus 3.76 N2, which is oxidizer air, in order to give MCO2 plus N over 2 multiplied by H2O. And in this case, if you have N2 is deleted as actually, is dealt actually with as an inert gas, fully inert gas. It does not react. So for the combustion, while writing down the combustion equation, we assume actually that N2 is an inert gas. However, Shabab, due to the heat release, here we should have some heat is rejected. This is all of this burning fuel or exothermic reaction. So with this heat, the temperature will be raised. And at higher temperature, as I told you, this N2 will be converted to actually the basic N plus N, and this N will react with O2 to form actually NO and NO2. But in all reactions, while writing down the combustion equation through this course, we assume, Shabab, that N2 is an inert gas. So here, the coming N2 will be leaving as N2. So here we have it will be M plus N over 4 multiplied by 3.76. This is actually N2. So N2 is coming with this number of moles, M plus N over 4 multiplied by 3.76, and it will be leaving with the same actually number of moles as an inert gas. This term, Shabab, which is M plus N over 4, we give it the symbol gamma or nu. This is actually gamma, Shabab, or nu. We call it actually the stoichiometric or theoretical coefficient, which is actually represent what, Shabab? The number of theoretical number of moles of air that are required in order to complete the combustion of the fuel. So it is just the theoretical amount of air required to complete combustion of the fuel. So we don't have, Shabab, either excess air or less air. Just we have the theoretical or stoichiometric. So theoretical or stoichiometric mean actually the number of moles of air that are just enough to convert the fuel, fully convert the fuel, convert the carbon into carbon dioxide, convert actually the hydrogen into H2O. We don't have, ya shabab, any intermediate component like carbon monoxide or hydrogen. All of these components, ya shabab, does not exist. We assume the full conversion of the fuel in this case. So gamma or stoichiometric coefficient, which is equal to m plus m over 4, represent actually the stoichiometric or theoretical number of moles of air that are enough, just enough, to convert actually the fuel from the hydrocarbon form to convert it actually to carbon dioxide plus H2O in this case. We call this combustion, shabab, as theoretical or stoichiometric combustion. Stoichiometric, that means we have just enough amount of air to completely convert the fuel. We don't have excess air, we don't have shortage of air, so just we have actually the theoretical amount. So we call it actually as the stoichiometric combustion in this case. And based on this, shabab, this is the air, number of moles of air. This is the air, and here is the shabab, here is the fuel. And we have actually in this case, based on that, we can calculate the air to fuel ratio by mass. We call it stoichiometric or theoretical, because we don't have excess air in this case, just we have the stoichiometric air. So the air to fuel ratio by mass is the mass of air divided by the mass of fuel. And the mass of air is equal to the number of moles of air multiplied by the molecular weight of air divided by the number of moles of fuel multiplied by the molecular weight actually for the fuel in this case. But what are the number of moles of air, shabab, in this case? Number of moles is equal to what? Air is O2 plus 3.76 N2. So the number of moles is equal to the gamma, which is m plus n over 4. So let's leave it as gamma or nu. So this is the number of moles multiplied by the molecular weight of air, which is O2, which its molecular weight is 32, plus 3.76 multiplied by the molecular weight of nitrogen, which is 28. Okay? Is that clear, shabab? This is the mass of air. Divided by the mass of fuel, we have the number of moles of fuel. We write down the equation for 1 kilomole of the fuel, multiplied by the molecular weight of the fuel, Cm. The molecular weight of carbon, which is 12, multiplied by the number of moles, which is m, plus the molecular weight of hydrogen, which is 1, multiplied by the number of moles of hydrogen, which is n in this case. And this air to fuel ratio by mass, because it is the mass of air divided by the mass of fuel, we call it a stoichiometric or theoretical, because we just have enough amount of air, the theoretical amount of air that can convert this fuel. This can be calculated in kilogram air per kilogram fuel in this case. Is that clear, Yeshua? Do you have a question?
Yes. Clear.
Anybody have a question, Shabab? So this is, Shabab, what we call the air to fuel ratio by mass. Now we have another air to fuel ratio that we can define, but it is rarely used. We call it actually the air to fuel by volume, or the molar air to fuel ratio, or air to fuel ratio by mole. So the air to fuel ratio by mole or by volume, which is equal to the number of moles of air divided by the number of moles actually for the fuel. Number of moles of air is equal to what, Shabab, from this equation? Equal to gamma.
Yeah.
Plus what? Multiplied by what? Air is only one molecule, or we have one O2 plus 3.76 N2. So 1 plus 3.76, which is 4.76. Divided by the number of moles of fuel, we wrote down actually the combustion equation per 1 kilomole of the fuel. So this should be divided by 1. And this is actually defined in kilomole air per kilomole per kilomole. This is the unit of air to fuel ratio by volume. So what is the relationship between air to fuel ratio by mass and the air-to-fuel ratio by volume. By mass is equal to number of moles multiplied by the molecular weight. So the difference here actually is what? Is the molecular weight. So the air-to-fuel ratio by mass is equal to the air-to-fuel ratio by volume, which is the number of moles multiplied by what? The molecular weight. So it is multiplied by the molecular weight of air divided by the molecular weight of the fuel. And this is the relation between the air-to-fuel ratio by mass and the air-to-fuel ratio by volume. Now, what is the molecular weight of air, Shabab? Molecular weight of air is equal to what? We said air is O2, 21% O2 plus 79% NO2. So it will equal to 0.21 multiplied by the molecular weight of O2, which is 32, plus we said the molecular weight of a gas mixture is equal to the summation of the mole fraction multiplied by the molecular weight of each component. So 0.21 multiplied by 32 plus 79.79 multiplied by 28. If you calculate this, it will be about 28.8 kilomole per kilogram. This is actually the molecular weight of air. Okay, so if you need it in any equation, the molecular weight of air 0.2132 plus 0.79 multiplied by 28. And this is how we can calculate the air-to-fuel ratio in this case. But usually, when you are burning a fuel, you cannot provide just the stoichiometric or the theoretical amount of air, which is equal to m plus n over 4. We have to add more air, because we don't guarantee actually that all fuel will be just mixed perfectly so that it can meet actually the corresponding amount of air, then it can be converted to the combustion product. So usually there is a problem of mixing between air and the fuel. We cannot mix perfectly the fuel with air, so that actually when we provide a stoichiometric air, just the theoretical amount of air, all of the fuel will be converted to combustion product in this case. So in this case, we have to add more air in order to make sure actually that all of the fuel. Is there a voice or something? So in this case, we have to add more air in order to make sure actually that all of the fuel will be converted to the combustion product. Here the combustion product we said plus gamma multiplied by 3.76 N2. This is for the complete equation for the theoretical combustion of air. So usually, Shabab, as I told you, we cannot provide just the theoretical amount of air in order to make sure actually that all of the fuel will be converted to the combustion product. So in this case, we have to multiply by a factor here, which is lambda. Lambda, we call it, Shabab, as the excess air factor. So lambda is the excess air factor, and it gives us indication about actually the amount of excess air existing actually for a given combustion equation in order to convert the fuel from the hydrocarbon form. It can be converted actually to the combustion product in terms of carbon dioxide plus water vapor in this case. So this lambda, Shabab, if it is actually greater than 1, that means actually we have excess air in this case. If we have excess air, the combustion, we call the combustion in this case as lean combustion. Lean combustion, Shabab, that means we have more air, more excess air than the theoretical air. So in this case, the fuel will be burned actually a much amount of air. We call the combustion in this case as lean combustion. This is actually if the excess air factor is greater than 1. If we have the excess air factor is equal to 1, in this case we call the combustion as actually stoichiometric or theoretical combustion in this case. So in this case, we just have enough amount of air in order to convert the fuel in this case. And in some cases, if lambda is less than 1, that will mean actually we have less amount of air, less than the theoretical amount of air required to convert the fuel. So in this case, actually we call the combustion as fuel-rich combustion. And in this case, we don't have enough amount of air in order to convert the fuel, fully convert the fuel. And in this case, the combustion, Shabab, will be what? will be incomplete combustion. So in case of the excess air factor is less than 1, in this case we call the combustion as fuel reach. Fuel reach is that mean we have excess fuel and we don't have enough amount of air. And in this case, as we have excess fuel, that means the combustion will be actually incomplete in this case, and the fuel will not be converted fully into carbon dioxide and H2O. In this case, some actually intermediate component like carbon monoxide and hydrogen will be existing in the combustion product in this case. Okay, but we can express the excess air factor either in theoretical air, we call it theoretical air, or we can express actually in excess air. Like if we say we have 200% excess air. If we have 200% excess air, that means actually lambda in this case is equal to 2, which is 200% excess air. Excess air more than the theoretical air. Theoretical air which is 1, so in this case lambda will equal to 2 plus 1 will equal to 3 in this case. But if I told you we have 200% theoretical air. Theoretical air, that means in this case the lambda or the excess air factor will just equal to 2 in this case. Okay, so if we have excess air, excess air, that means actually excess more than the theoretical air. Theoretical air at theoretical air, lambda is equal to 1. If we have 200% excess, so lambda will equal to 2 plus 1. If we have 200% theoretical air, that means lambda is equal to actually just equal to 2. So either we can express it in terms of theoretical air, or we can express it actually in terms of the theoretical air in this case. So if we have a shabab, lambda in this equation will give us indication about the actual amount of air. If lambda is greater than 1, then we have excess air. If this parameter or coefficient is less than 1, that we mean actually we have fuel reach and we have less amount of air in this case. So in the actual combustion in this case, we can calculate the air to fuel ratio actual by mass. In this case, this air to fuel ratio will equal to what, shabab? The number of moles of air is equal to what? Lambda multiplied by gamma, which is m plus n over 4. This is actually the number of mole of gas for the actual combustion, multiplied by the molecular weight, which is 32 plus 3.76 multiplied by 28. This is actually for the air. What about the fuel? We have 1 kilomole of the fuel multiplied by the molecular weight of carbon, which is 12 multiplied by m plus 1 multiplied by n in this case. And we call the air to fuel ratio in this case as what? As the actual air to fuel ratio. Because in case of actual combustion, usually we try actually to provide excess air more than actually the theoretical amount of air. Then in this case, we have to multiply by the excess air factor. We provide excess air in order to make sure actually that all of the fuel would be converted to carbon dioxide plus H2O, and we don't have any kind of intermediate product like carbon monoxide or hydrogen or any kind actually of intermediate product. And in this case, the air to fuel ratio actual will equal to lambda, the excess air factor, multiplied by gamma, which is a stoichiometric coefficient, which is m plus n over 4, multiplied by the molecular weight of air divided by the mass of the fuel, in this case. But what is the difference, Shabab, between the theoretical and the actual air to fuel ratio? What is the difference between both of them? If we divide the actual air to fuel ratio by the theoretical air to fuel ratio, it will be what, Shabab?
The excess air factor.
Exactly, it will be the excess air factor. So just the theoretical, air to fuel theoretical, it is the same equation, but just lambda was equal to 1. If lambda is equal to 1, we call it a stoichiometric or theoretical combustion in this case. And in this case, the air to fuel ratio is the air to fuel ratio theoretical. But in actual combustion, we try to add more air through the excess air factor in order to make sure that all of the fuel will be converted to product in this case. Okay, so this is air to fuel ratio actual. So if we divide the air to fuel ratio actual by the air to fuel ratio theoretical, that should give us actually the excess air factor. And this is the definition, Shabab, of the excess air factor. excess air factor, lambda, is equal to air to fuel ratio actual divided by the air to fuel ratio theoretical or stoichiometric for the theoretical combustion. Okay? Or we can say, Shabab, it is the fuel to air ratio actual. So either air to fuel actual or air to fuel theoretical or fuel to air theoretical divided by fuel to air actual. But usually, Shabab, in the combustion actually society, you will not find actually the excess air factor is used actually extensively. Usually they are using another parameter which is just equal to 1 over the excess air factor, or the excess air factor is equal to 1 over phi. Phi is representing the equivalence ratio. So the equivalence ratio, Shabab, is not a new parameter. Just it is equal to 1 over the excess air factor. And this parameter, Shabab, the equivalence ratio, is used actually extensively in the combustion society. So if you are involved in the combustion research, or if you have read a paper about combustion, you will find usually the air to fuel ratio is represented actually by the equivalence ratio, not by the excess air factor. Okay? So the excess air factor is equal to 1 over the equivalence ratio, or the equivalence ratio is equal to 1 over the excess air factor, and it is equal to fuel to air ratio actual divided by fuel to air ratio theoretical, or it is equal to air to fuel theoretical divided by air to fuel ratio actual. So it is just the reciprocal actually of lambda 1 over lambda. So it will be air to fuel theoretical divided by air to fuel actual. If this lambda, Shabab, is this phi, sorry, if this phi is equal to 1, we call the combustion as a stoichiometric, or we call it actually theoretical combustion, stoichiometric or theoretical combustion, if phi is equal to 1, like lambda. And in case of phi equal to 1, lambda should equal to 1. But in case of phi less than 1, that means lambda is what? Lambda is greater than 1. So we have excess air in this case. And the combustion in this case, we have lean burning, or we have actually lean combustion in this case. And usually, as I told you, we prefer to work with lean combustion, slightly lean. So usually in gasoline engine, lambda is about 1.01 or something, or 0.02. So just a little bit more excess air in case of gasoline engine, in order to make sure that all of the fuel will be converted to combustion product and we have complete combustion of the fuel. Also, Shabab, in some application like gas turbine, usually we work extra lean. So usually in this case, lambda, it may go actually to 300% excess air. So we have excess air more than the theoretical by 300%. So that means in this case, lambda may be equal to 4 or 3 or something. But in case of gas turbine, Shabab, we provide more excess air around the combustion chamber in order to cool down the combustion product. Because the combustor in the gas turbine, the combustion product will be passed through actually a turbine. It will hit the blade of the turbine in order to generate shaft power or something. And those blades actually have a limiting temperature. So we have to cool down the combustion product. So usually we cool down the combustion product through actually providing excess air. So in case of gas turbine, it works actually extra lean. We have more excess air in this case in order to cool down the combustion product in this case. So if phi is less than 1, that means lambda is greater than 1. That will mean we have excess air, so we have lean combustion. So it is the reverse of lambda, or if phi is greater than 1, that means actually in this case lambda will be less than 1. So we have actually in this case less amount of air, and the combustion in this case will be fuel-rich combustion or incomplete combustion in this case, because we don't have enough amount of air. Okay, is that clear, Shabab? Is it clear? Ali, do you have?
Yes.
So have you had an idea about this before, or the mechanical student guys?
Yes.
The air ratio, maybe. The other one,
So you have an idea.
Yes.
So maybe I should go faster. Huh? So this is
No, this is good. This is good.
okay. So this is يا شباب how to calculate يعني the air to fuel ratio. Usually we don't represent it in terms of air to fuel ratio. We represent actually in terms of air to fuel actual divided by air to fuel theoretical, which can be either represented by the parameter excess air factor lambda or the equivalence ratio, which is 1 over lambda. So this parameter شباب phi give us indication about the quality of the mixture, the ratio between air to fuel for a given mixture. As I told you, in gasoline engine usually it works slightly lean, but in case of diesel engine يا شباب, is it slightly lean or we have to add more air? For diesel engine compared to gasoline, should we provide more air or less air?
Because,
Should be more air?
yes.
Yes, because يا شباب in diesel engine, as you know, we inject the fuel by the end of the compression stroke. So the piston is going up the second stroke, and we just inject the fuel. So there is limited time for this fuel to mix with the air and to complete the combustion. This is during the end of the compression stroke and during the expansion stroke. So in this case, we have to provide more air in order to make sure actually that all of the fuel will have enough amount of air. Okay, there is a problem of time. That fuel does not have time, unlike the case of gasoline. In case of gasoline, we inject it with the intake stroke, and it is through the whole compression stroke, so they are mixed very well. But in case of diesel engine, the time is limited. We inject the fuel at the end of the compression stroke. So we have to make sure, apply more air in order to make sure actually that the fuel will not have a problem with air. Just it has its own problem. It has a problem with time. And that's why diesel engine cannot run actually at higher RPM, because the fuel need time to self-ignite, to mix with air and self-ignite, and then we can generate power. Okay? So in this case, we have to provide more air in order to completely convert the fuel and also to reduce the emission. So in fuel, diesel fuel is a heavy fuel, so we have to apply more air in order to make sure actually that we don't have extra excess emission in this case. But this is how to calculate the air to fuel ratio, actual air to fuel ratio theoretical, and how to calculate the equivalence ratio in case if we have a single hydrocarbon or a hydrocarbon fuel of the chemical structure CmHn. But let's say the second case actually if we have mixture of hydrocarbons. Let's say we have two fuels, CM1HN1 plus CM2HN2. Let's say we have the two fuels by the ratio 1:1 by volume. 1:1 by volume, that means we have, if we have 1 kilomole of the fuel, that means we have 0.5 kilomole of the first fuel plus 0.5 kilomole of the second fuel. So usually we write down the equation per 1 kilomole of the fuel. So if we have two fuels, ratio 1:1 by volume, that means we have 0.5 kilomole of the first fuel plus 0.5 kilomole of the second fuel. Like this, plus I will just say lambda, the excess air factor, plus gamma, which is m plus n over 4. The oxidizer is O2 plus 3.76 Me2, and that should give us what, Shabab? That should give us m CO2 plus n over 2 H2O plus. If this lambda is greater than 1, Shabab, that means we have excess oxygen in this case. So if it is greater than 1, we have excess oxygen. If it is equal to 1, that means all of the oxygen will recombine with the fuel and it will be converted to CO2 plus H2O. But if it is greater than 1, then we should have excess air in the combustion product, which should equal to lambda minus 1, because this one will be used in burning the fuel. So if we have more than 1, so we should have lambda minus 1 multiplied by the number of moles of O2, which is gamma O2 plus lambda N2 will be leaving the same, lambda by gamma multiplied by 3.76 N2 in this case. But what about M? What about N? What about gamma? The parameter gamma يا شباب is equal to M plus N over 4. M is the number of moles of carbon atoms, N is the number of moles of the hydrogen. طيب, the number of moles of carbon atoms in this case is equal to what يا شباب? 0.5 multiplied by M1 plus 0.5 multiplied by what? Is it يا شباب? Is it? طيب, what about N? Number of mole of hydrogen atoms is equal to 0.5 N1 plus 0.5 multiplied by N2. And in this case, gamma will equal to M plus N over 4. And in this case, the air to fuel ratio actual should equal to the same, lambda by gamma multiplied by 32 plus 3.76, 28 divided by, in this case we have 1 kilomole, but it is 0.5 multiplied by CM1, so 12 multiplied by M1 plus 1 multiplied by N1 plus 0.5 for the second fuel, 12 by M2 plus 1 multiplied by N2 in this case. And this is the air to fuel ratio, by mass in this case. But if we have, let's say 3 fuels. So let's say 3 fuels, 0.3, 0.3, and 0.4. This is the mole fraction of each fuel. So I will say 0.3 CM1 HN1, 0.3 CM2 HN2, 0.4 CM3 HN3. Okay, and this is actually 1 kilomole of the fuel. Was the same, I will be writing the equation the same form, lambda, gamma, and all of the other components actually in the combustion problem. But in this case, gamma will equal to what? M plus N over 4. And in this case, M should equal to 0.3 M1 plus 0.3 M2 plus 0.4 multiplied by M3. And like this, we can calculate the factor N in this case. This is the air to fuel ratio actual by mass. This is by mass يا شباب. And by volume should equal to what يا شباب? Air to fuel ratio by volume should equal to lambda multiplied by gamma multiplied by 4.76 divided by the number of moles of the fuel, which is 0.5 plus 0.5, which is 1 in this case. Is that clear يا شباب? Is it clear?
Yes.
So this is a the case if we have mixture of hydrocarbon. Like let's say if we have alcohol fuel. Alcohol fuel, it is oxygenated fuel, and it is used as a fuel additive, as I told you, in gasoline engine in order to improve the octane number. So usually we use the alcohol fuel. But in this case, if we have alcohol, how we can write down the combustion equation and how we can calculate the air to fuel ratio in this case. The third case, if we have alcohol fuel. Alcohol fuel usually has a chemical composition CmHn, let's say OZ. Okay? So alcohol fuel like methanol يا شباب CH3OH or ethanol C2H5OH, those are kind actually of alcohol fuel. We have carbon plus hydrogen plus oxygen in this case. So we have to reorganize the alcohol structure in order to be in this form, CmHnOZ. So here we have C2, like in this case ethanol, it will be C2H5OH. So we have H5 plus 1 will be H6O. So this is the equivalent of the ethanol. Then I can write down the combustion equation. If we have 1 kilomole CmHnOZ, I think this is a kind of some traditional information for you that should equal to lambda by gamma O2 plus 3.76 N2. That should give us actually MCO2 plus N over 2 CO2 plus lambda minus 1 gamma O2 plus lambda gamma 3.76, all of this N2. So what about this gamma? Gamma, we should actually, for the hydrocarbon fuel, is M plus N divided by 4. This is the amount of oxygen required to convert actually the hydrocarbon fuel. But this is the amount of oxygen required, but the fuel itself, it contains some oxygen. So we have to subtract this oxygen. So we have Z from O, that means it is Z over 2 from O2. And this is a parameter gamma, which is M plus N over 4 minus Z over 2. Z actually is the number of moles of oxygen in the fuel in this case. And the same air to fuel ratio by mass, it is the same lambda by gamma, the same 32 plus 3.76 N2 divided by the fuel, which is 1 multiplied by 12 by M, 1 by N plus 16 multiplied by Z. Okay? And this is the air to fuel ratio. We have actually, if we have an alcohol fuel. Is it clear, Shabab?
I think there is a typo. You mean N over 2 H2O, right?
Here? Yes. Thank you. So this is Shabab N over 2 H2O. Yes. In the combustion product. Yes.
Why do we write lambda minus 1 in the oxygen?
In the oxygen here, because if lambda is equal to 1, then we have theoretical combustion. Just we have enough amount of oxygen that will be converting the fuel. Gamma is M plus N over 4. So M will be converting the M carbon to M carbon monoxide. And the N over 2 will be converted, N hydrogen will be converted to N over 2 H2O. And in this case, if lambda is equal to 1, so this is lambda minus 1. If lambda is equal to 1, then it will be 0. We don't have excess oxygen in the combustion product. In case if lambda is equal to 1, because the amount of oxygen existing is just enough to convert the fuel into carbon monoxide plus hydrogen. If we have excess air, more than the theoretical, so part of this oxygen will be converting the fuel into carbon monoxide plus hydrogen, but the excess oxygen will be leaving in the combustion product. And that's why, if it is lambda is greater than 1, then in this case, we should have some O2 in the product. So it should be lambda minus 1. If it is greater than 1, then we can have some O2 in the product. If it is equal to 1, then in this case, O2 is not existing in the product. Okay? And that's why, Shabab, as I told you, we have to add more air or more oxygen in order to make sure that all of the fuel will be converted to carbon monoxide, carbon dioxide plus H2O to make sure full conversion of the fuel. Plus, we may have excess oxygen, plus for sure excess nitrogen. That should cool down the combustion product. It should reduce actually the temperature of the combustion product in this case. And this is a parameter, Shabab, in order to control actually the emission. Because usually at higher temperature, as I told you, nitrogen will dissociate at higher temperature to NO plus NO2, and this should result actually in the NOx emission. Okay? And one mechanism, Shabab, is to reduce NOx emission is to burn using excess air. We can add more air in the combustion process. So in this case, we will have excess air in the combustion product. It will cool down the temperature of the combustion product. So that actually prevents the dissociation of nitrogen to be dissociated to NO plus NO2 and result actually in the NOx emission. So usually we need the combustion product nitrogen to be in the nitrogen form, not actually in the NOx form. Okay, so if we are able to reduce the temperature of the combustion product, we can reduce actually the NOx emission. We call it thermal NOx. Thermal NOx is the NOx created due to the dissociation of nitrogen to form NO plus NO2. Is that clear, Shabab? Yes, Mustafa?
I have a question. The air to fuel ratio, is it the mole or the mass?
This is the mass, or what we're talking about here, this is the mass, because it is the number of moles multiplied by the molecular weight. Number of mole is lambda by gamma multiplied by the molecular weight, which is 32 plus 3.76 multiplied by N2. Air to fuel by volume, usually شباب, and in practice we use air to fuel by mass. If you need to calculate air to fuel by volume, the number of moles. Number of moles of air is lambda by gamma multiplied by 1 plus 3.76, which is 4.76, divided by the number of moles of fuel, which we usually write down the equation for 1 kilomole, which is 1 in this case. Okay. We can. Sorry, Mustafa.
عندي سؤال ثاني.
Yes, اتفضل.
الاير تو فيول ريشيو وش الفائدة منه؟ what is the يعني
It gives us indication about the quality of the mixture. As I told you, in case of gasoline engine يا شباب, in case of diesel engine, we said diesel engine control actually the engine operation through controlling the amount of fuel, and the amount of air is fixed. So that means in case of diesel engine we call it quality control, because it controls the quality of the air to fuel mixture, the air to fuel ratio, by changing actually the amount of fuel injected. So each time, depending on the load, it varies actually the amount of fuel injected. And usually we can say we have almost a fixed amount of air. That means in this case the fuel to air ratio will be changed in this case. And that's why in case of diesel engine we call it quality control, because we control the quality of the mixture. The quality of the mixture, which is the air to fuel ratio. So usually, شباب, to have combustion, let's say like this room, if we have certain amount of fuel in this room, and this, I just get inside this room and just try actually to make ignition. Will this room burn out? Will it explode?
No.
Will it start a combustion?
No.
Let's say we have a fuel tank just beside your car. There is a fuel tank. Let's open it, okay? And let's try to ignite outside this car. Not inside the tank, but outside, a little bit away. Will it ignite? We have fuel and we have air, and I started the ignition, but it does not ignite. Why? Because the fuel to air ratio is not actually in the proper range. We have the flammability region. Flammability region is the region in which we can have combustion. So there is a limit of the air to fuel ratio. So we cannot increase lambda to be actually for infinity in both sides, either greater than 1 or less than 1. No. In this case, you cannot get combustion, because the air to fuel ratio has to be within a given limit. We call it the flammability limit. So to have a combustion, we have to have the air to fuel ratio around the theoretical value in order to start the combustion. Otherwise, the combustion will not be starting in this case. So we have to control this ratio in order to have combustion of the fuel. So usually this fuel to air ratio شباب is around the theoretical value. Okay. طيب, this is what we said. The combustion is reactant, and we have a product. And as I said, we have the fuel has to be ignited يا شباب. Either the fuel is spark ignited like a spark ignition engine, it can be self ignited like the case of the diesel engine. So we have to have fuel, we have to have the oxidizer, and we have to have ignition. This is the triangle actually to have combustion. In addition, the air to fuel ratio has to be actually within the flammability limit of the fuel. Air to fuel ratio should be very close to the air to fuel ratio theoretical. طيب, this is about what we said. Air is 21% O2 plus 79% N2 by volume. So if we just divide it by 21, so each 1 kilomole of O2 should have 3.76 kilomole of nitrogen. But if we consider by mass, air is considered actually as 23% by mass oxygen and about 76% nitrogen in this case. We can convert from mole fraction, we can convert to mass fraction. We have already given you the equation to convert it. If we get the mass fraction of oxygen and the N2 in air by mass, it will be 0.23 and it will be 0.76. If we divide by 0.23, then in this case, each kilogram of oxygen in the air should have 3.29 kilogram of nitrogen in this case. Okay, this is يعني يا شباب for your knowledge, because what we are concerned about actually is the molar ratio, because we write down the combustion equation in terms of actually per 1 kilomole of the fuel. We don't care actually about the kilogram. Okay. طيب in some cases يا شباب like Oxy Combustion, usually we don't have O2 plus nitrogen. Usually we have O2 plus some recirculated carbon dioxide. Or in some cases يا شباب, usually we burn with air, but in order to improve the combustion, usually we add some pure oxygen to the air. As I told you, pure oxygen is a little bit expensive to have pure oxygen. But يعني in some cases we can enrich the air with some oxygen. We can add a little bit more oxygen with the air in order to improve the combustion. And in this case, the ratio will not be O2 plus 3.76, because the ratio 21% in this case will be changed in this case. So how we can write down in this case, شباب, the oxidizer formula? We said this is the fuel. Let's say 1 CmHn plus lambda multiplied by gamma. We said the air in this case is 21% O2 plus 79% N2. If I divide it by 21, so it will be the oxidizer will be O2 plus 79 divided by 21, it will be 3.76. But let's say the concentration of oxygen, we have oxygen enriched air. Let's say we have the concentration of oxygen is 30% oxygen, plus let's say 70% nitrogen. So what will be the oxidizer in this case, شباب? O2 plus what?
70 over 30.
Exactly. 70 شباب is what? Is the mole fraction of nitrogen divided by what? The mole fraction of oxygen. Well, this is actually for the nitrogen, and this should be actually our oxidizer in this case. And the same, it will be lambda by gamma the same way. But in this case, the oxidizer will not be O2 plus 3.76. No, in this case, in case of oxygen enriched combustion, O2 is not 21. Let's say if it is 30, then in this case, or any concentration, it will be the oxidizer will be O2 plus the mole fraction of nitrogen divided by the mole fraction of oxygen in this case. Is that clear يا شباب? But if it is carbon dioxide, so it doesn't matter. Here, instead of nitrogen, in case of oxy combustion, we don't have nitrogen. Usually we recirculate some amount of CO2. So here, instead of nitrogen, it will be CO2. And here, actually, this is the mole fraction of CO2 divided by the mole fraction of O2. Let's say we have oxidizer, 30% O2 plus 70% CO2. So the oxidizer will be O2 plus YCO2 divided by YO2 from the CO2. So whatever this ratio, you can just make it. And in this case, the combustion product will be lambda minus 1, the same by gamma O2, plus instead of nitrogen, CO2 is considered as inert gas as well. So it will be in the product lambda by gamma multiplied by this ratio, which is YCO2 divided by YO2 from the carbon dioxide, which is CO2. Okay, is that clear, شباب? So this is the generalized equation for the oxidizer, and it may come to your exam. Okay, so it may not be 3.76. So in case of oxy combustion, we don't have nitrogen, just we have carbon dioxide. Then in this case, we can write down the oxidizer based on this expression. Or in some cases, as I told you, if we have oxygen enriched air, then in this case, the concentration of oxygen will be changed. Then we have to change the way we write down the combustion equation. Type the assumption in this case, شباب, we assume that N2 is perfectly inert gas. It will be just N2 coming in and leaving as N2. Air is dry. We don't have water vapor in this case, and the air is assumed actually 21% O2 plus 79% N2, unless otherwise mentioned. Like in case of oxy combustion, oxygen enriched air, if we have a change actually in this composition, I will just let you know in a given problem. Type the combustion fundamental يا شباب, the chemical equation should be balanced based on the number of moles or mass. whatever actually mass cannot be created or destroyed. So the number of mole of a given species at inlet should be the same as at outlet, and also the number of mass, the mass value should be actually equal for the reactant and for the product. To ignite the fuel, شباب, to start the combustion, we have to have ignition of the fuel, and the fuel has to reach its ignition temperature. The ignition temperature for gasoline is about 280 degrees Celsius. For diesel, it is a little bit actually lower, because diesel actually has more ability to self-ignite. For carbon, it is 400, and you can see actually for other component here, you can see this is the ignition temperature of the fuel. The temperature at which the fuel should reach in order to start the combustion. One more condition to have the combustion is that the air to fuel ratio must be actually within the flammability region. Air to fuel ratio should be around the theoretical value, either higher or lower, but it should not be actually away from the theoretical value. Yes, Mustafa?
About the minimum ignition temperature.
Yes.
يعني كان عندنا temperature أقل من 280 for gasoline, we cannot ignite it.
Yes, we cannot ignite gasoline at lower temperature than 280.
حتى بالسبارك ولا
هو السبارك نفسه سبارك يا شباب is a combustion. Spark in this case we have high temperature. So usually when numerical modeling or something, when we do numerical modeling, in order to start ignition in the numerical modeling or numerical calculation, we have to create a zone of high temperature, higher than the self-ignition temperature. We have to initialize the calculation from higher temperature so that the model can understand actually that there is ignition. So the ignition source يا شباب should be at higher temperature than this value. Okay? Still have a question, Mustafa?
Yes. لا.
It's okay. So this is Shabab, as I told you, we have talking about this carbon, each carbon molecule need O2 to convert to carbon dioxide. This is by mole, number of moles should be equal. If it is by mass, then we have 12 kilogram of carbon. 12 is the molecular weight multiplied by the number of moles, which is 1. So 12 kilogram of carbon plus 32 kilogram of O2 should give us 44 kilogram of carbon dioxide. Like this hydrogen, if we have some sulfur in the fuel, but usually the fuel should be subjected to desulfurization process, because sulfur can cause actually the production of SO3, and if it is released to the atmosphere with water, it can convert actually to H2SO4, or it can cause actually the acid rain in this case, which is the sulfuric acid. But anyway, if we have sulfur in the fuel like the coal or something, it has to be converted to SO2. This is يعني شباب all what we said. This is the equation on mole basis and mass basis. If we are burning with nitrogen, then we can add nitrogen. It is an inert gas and it will be leaving with the same concentration. Complete combustion يا شباب, if fuel is converted fully to carbon dioxide, H2O, and if we have sulfur, it has to be converted to SO2. But incomplete combustion, in this case, we don't have enough amount of air, so part of the fuel will be converted to carbon dioxide, but still some carbon will be converted to carbon monoxide because it does not find actually enough oxygen to be converted to carbon dioxide. And we may have soot in the exhaust emission, especially in case of diesel engine. It is very rare, ya shabab, to have hydrogen in the combustion product because hydrogen is highly reactive and it competes actually with carbon monoxide, and usually it wins. So when there is one oxygen molecules and we have hydrogen atom plus carbon monoxide atom, the hydrogen atom will accept it and it will take this oxygen first and it will be converted to water vapor. So usually we will have, if in case of incomplete combustion, usually we have carbon monoxide but we don't have hydrogen. So what are the reasons for incomplete combustion? If we have insufficient amount of air, we have actually a less amount of air, less than the theoretical value. Or if we have insufficient mixing, we don't have the fuel, it does not mix properly with air. So whatever, if it is, even if we have excess air and we don't have good mixing, that means actually some fuel will be leaving in the combustion product in this case. Dissociation at higher temperature, usually the gases like carbon dioxide dissociate actually to CO plus O, and in this case we may have carbon monoxide in the product. If we have actually elevated combustion temperature, the combustion product will be dissociated back to have the initial or intermediate component, like carbon monoxide and the hydrogen in this case. Usually, in case of incomplete combustion, you will have this reddish actually flame, due to the existence of carbon monoxide and the soot, usually they result actually in a kind of reddish flame. But if it is like the stove at your home, if it is a blue shape, that means we have in this case a complete combustion. You can actually control actually the shape of this flame. Even if you have a stove working with gaseous fuel at your home, in this case, you can control the amount of fuel flow rate in order actually to control the shape of the flame. If it is blue, that means we have complete combustion, we don't have carbon monoxide. But just try to avoid actually the reddish color, because that is actually a clear indication that there is soot and there is actually incomplete combustion, and we may have actually some carbon monoxide in this case, which is a toxic gas. Okay. Type theoretical air, theoretical, which is actually just enough amount of air, gamma is n over 4. Like if we have methane, burn it theoretically with air, O2 plus 3.76 N2. So gamma will equal to M, which is 1, plus N over 4. N is equal to 4, so 4 over 4 will be 1, so 1 plus 1 will be 2. For case of isooctane, M plus N over 4, so it will be 8 plus 18 divided by 4, which is 4.5, so all it will be 12.5. This is actually the theoretical amount of oxygen required in order to convert the whole fuel, C8H18, to convert it actually to carbon dioxide plus H2O. And N2 is an inert gas coming in and it is leaving the same. This is how we define the air-to-fuel ratio. Air-to-fuel ratio by mass and the air-to-fuel ratio by volume, and the difference between both of them is the molecular weight. Here is an example, Shabab. He said calculate the theoretical air. When he says theoretical or stoichiometric, that means lambda or excess air factor is equal to what? Equal to 1 in this case. Equal to 1. And the equivalence ratio is equal to 1. So if we have fuel C8H18, so in this case M is equal to 8 and the number of hydrogen atom is 18, so gamma M plus N over 4, it will be 12.5. Then we can write down the combustion equation, C8H18 plus gamma 12.5 O2 plus 3.76 N2. That should give us M CO2. M is equal to 8, so it will be 8 CO2 plus N over 2. N is 18 over 2, it will be 9 H2O plus the same gamma multiplied by 3.76. This is actually N2, which is 3.76 multiplied by 12.5. Then we can calculate air-to-fuel ratio by mole, which equal to 12.5, which is gamma multiplied by 1 plus 3.76. Okay, divided by the number of moles of the fuel, which is 1. Air-to-fuel by mass, which will equal to lambda, is equal to 1 in this case. We have theoretical air. Gamma is 12.5 multiplied by the molecular weight of air, which is 32 plus 3.76 multiplied by the molecular weight of nitrogen, which is 28. Divided by the mass of fuel, the number of moles of fuel is 1 multiplied by its molecular weight. We have 8 multiplied by 12 plus 18 multiplied by 1. Then we can calculate the air-to-fuel ratio. Usually, Shabab, as I told you, the excess air factor. Usually we have excess air in order to make sure that the combustion is complete, and in order actually to control the combustion temperature. We have to lower down the combustion of the temperature of the product or the exhaust gases, and in this case we have to burn or add actually more air for the combustion in this case. We express the excess air factor in terms of excess air or theoretical air. So example here, Shabab. If we have 0% excess air, that means we have 100% theoretical and lambda is equal to 1. But if we have 20% excess air, that means we have 120 theoretical air and lambda is equal to 1.2. So lambda is equal to 1 plus the percentage actually of the excess air. Unlike this, if we have 200% excess air, that means we have 300% theoretical air and lambda is equal to 2 plus 1 in this case. Okay, so here it is. If we have 0% excess air, so lambda is equal to 1. We have theoretical air in this case. But if we have 20% excess air, That means we have 120% theoretical air, and lambda will equal to 1 plus 0.2, which is 1.2. If we have 200% excess air, so lambda will equal to 2 plus 1, which is 3 in this case. So either we say it theoretical air or excess air, and the difference actually is 100%. Okay, is it clear, ya shabab?
Yes, clear.
Sorry. This is lambda is equal to 1 over the equivalence ratio. So usually we use the parameter equivalence ratio more frequently than the case of the excess air factor. Here, if we have single hydrocarbon, we have learned that. And this is يعني شباب an example. We have 1 kilomole of octane. So let's solve this example. And يعني it's something very simple يعني شباب. And I will end up with this. طيب here in this case يا شباب, he said we have isooctane and its chemical structure. You should be aware actually when I say isooctane, you should be able to configure that the chemical composition of the fuel is C8H18. So I may give it to you or not in your exam because we have taken a chapter and they should be aware of it. Okay. So he said we have isooctane C8H18 is burned with 20 kilomole of oxygen. So we have 20 kilomole of air, which is O2 plus 3.76 N2. In this case, he didn't provide us the value of the excess air factor. He just gave us actually the number of moles of air. And he said actually this number of moles, 20 kilomole, is burned with 1 kilomole actually of, in this case, actually of isooctane. So how we can write down the combustion equation? So usually we write it CmHn, and then we have MCO2 plus N over 2H2O. But all of this is about by knowing the lambda or excess air factor. Here he didn't give the excess air factor. So let's say we have alpha CO2 plus gamma H2O, alpha plus beta, let's say, to make it convenient, plus gamma, let's say O2 plus alpha, beta, gamma, let's say any parameter, delta N2. Okay, so can we make it like this, Ashwab? And in this case, we can just make balance. So make carbon balance for the carbon atoms. So we have 1 multiplied by 8. That should equal to the carbon in the product. We have alpha. That should equal to alpha. And in this case, the alpha should equal to 8 in this case. Okay. Type. What about, let's say, hydrogen balance? Balance for the hydrogen atom. So we have 18 in the reactant, hydrogen, and then the product we have beta multiplied by 2. Then in this case we can calculate beta should equal to 9 in this case. And let's have also O balance. Just to make sure if it is O2 balance or O balance, because in this case it will be different. So we have 2 multiplied by 20, which is 40. That should equal to 2 multiplied by alpha, 2 alpha, and CO2 plus O2 plus beta here, plus gamma O2 plus gamma. We have alpha plus beta, then we can calculate in this case gamma. And also we can make a balance, let's say for N2 balance, we can make here for N2 it will be 20 by 3.76, that should equal to delta. And in this case we can calculate alpha, beta, gamma, and delta. We can calculate all of these parameters, and here we can write down the combustion equation. But what about the air to fuel ratio, Shabab? Air to fuel ratio by mass will equal to the number of moles, which is 20 multiplied by 32 plus 3.76 by 28 divided by number of moles of the fuel is 1 multiplied by the molecular weight, which is 12 by 8 plus 18 by 1, and that should be the air to fuel ratio actually. That 24.1. This is actually the actual air to fuel ratio. طيب we need to calculate يا شباب lambda or excess air factor. Lambda is equal to what يا شباب? How we can get lambda? How we can get it يا شباب? So if you remember, when we write down the equation 1 per kilomole of the fuel, here يا شباب we said this 20 should equal to what? Lambda multiplied by what? Lambda by gamma. So usually we write down the equation per kilomole of fuel, we say plus lambda gamma O2 plus 3.76 N2. So that 20, if we have the number of moles of the fuel is 1, this number should equal to lambda by gamma. And gamma is equal to M plus M over 4. For this fuel, M is 8 plus 18 over 4. That should equal to 12.5. So gamma is 12.5 and this is 20. Then we can calculate lambda, it will equal to 1.6. And the 5 will equal to 1 over lambda. 1 over 1.6 it will be 0.625. This is the equivalence ratio. Is that clear, Shabab? Clear? Type, is there another way to calculate lambda? This is the air to fuel ratio actual. So lambda is the air to fuel ratio. Actual divided by air to fuel ratio. Theoretical, we have calculated air to fuel ratio actual. Here it is. How we can calculate air to fuel theoretical? I will be just writing the theoretical equation for the fuel C8H18. It will need actually gamma, which is x plus m over 4, which is 12.5, O2 plus 3.76 N2. This is the theoretical combustion. We have gamma, we don't have lambda in this case. And in this case, air to fuel ratio theoretical will equal to 12.5 multiplied by 32 plus 3.76 multiplied by 28 divided by 1, 18 by 8 by 12 plus 18 multiplied by 1. And this is the theoretical air to fuel ratio. If you calculate it, it will be about 15.06. So if I need to calculate the theoretical air to fuel ratio, just write down the theoretical combustion equation and calculate the air to fuel theoretical. Then if we divide 24 divided by 15, then you can get lambda.